Good evening, everyone, and thank you for joining us tonight. My name is Megan Neer, and I'm pleased to welcome you to the sixth installment of PNNL's live virtual community tour series. This 8-week series is intended to introduce you to the spaces and instruments behind the science and impact of Pacific Northwest National Laboratory and the world-class research that is taking place right here in the communities in which we live and work. PNNL is one of 17 Department of Energy national laboratories. At PNNL, we are advancing scientific frontiers and driving innovations that enable sustainable energy and enhance national security. Chemistry, earth sciences, data science, and biology are foundational at PNNL and underpin not only our scientific discovery, but our applied work as well. Our work to advance sustainable energy includes focusing on decarbonization and energy storage. And our national security expertise enables impact related to nuclear materials and threat analysis. We have about 5,300 staff and a diverse research portfolio that drives about $1.2 billion in business each year. Last year, we had nearly 1,300 peer-reviewed publications and 340 invention disclosures. Now that you've heard just a little bit about PNNL, and I'm sure some of you have heard this before at other virtual seminars, I'd like to move right into the tours. At this time, you will hear from Rebecca O'Neill, who will give you a brief introduction to tonight's tours. Rebecca is an advisor in the renewables group at PNNL. She joined the laboratory in 2015, and her research interests relate to energy justice, energy storage, community scale innovation, sustainable hydropower, and marine energy development. Rebecca.
Thanks, Megan. Hello, everyone. Welcome to the tour. My name is Rebecca O'Neill, as Megan said, and I lead a renewable energy team within the Electricity Infrastructure Division at Pacific Northwest National Laboratory. So PNNL is well known among our peer laboratories and our federal research partners as a leader in the evolution of the future electric grid. And we're really proud of this reputation. We're still growing. We have over 350 staff within our Electricity Infrastructure Division alone. And for reference, this is one of the largest concentrations of power system engineering research in the United States. And it's all right here at PNNL. So as you'll learn from the speakers here, we take our research from the heartbeat of the electric system all the way to the very edge of the grid. We have researchers who are working to make today's system run smoothly, as well as radically reimagining future electric system operations, poles and wires, communication, interoperability. And as you'll hear about in detail today, we are very focused on bringing new energy storage technologies to that future grid. So why energy storage? One of the wonders of our electric grid is that right now it works without significant energy storage. We are balancing electricity production with the changes in electricity demand, all of the electric loads and devices in our homes and businesses. PNNL believes that energy storage is the innovation linchpin to achieve decarbonization. And this means that our research agenda for storage has a huge wingspan. We are developing and scaling up new fundamental electrochemistries and technologies to be safer, use abundant and available components, and have a longer operating life for storage systems, all the way to a new vision for an electric grid with energy storage embedded widely, which would make the grid stronger, more capable, and simpler to operate as we add new layers of operational complexity. And then we take all of that insight about the technologies and the operations out to our partners so that the financial and the regulatory environments around storage innovation will be ready for the development. We're even thinking about the role of energy storage in advancing energy equity so that all electric customers can benefit from innovation and a better grid. In my shop, in renewables, we get at some of the tricky issues around renewable energy. In particular, I want to talk about predicting when renewable power plants will be fueled with a great deal of precision, and then having enough flexibility in the electric system to take advantage of all of those natural peaks and valleys in renewable resources. I'll give you an example. Offshore wind innovation. PNNL operates a LiDAR buoy program that launches advanced atmospheric sensors and instruments into a buoy in the ocean for seasons up to a year. And that all helps us learn about offshore wind characteristics and potential. On our side, on the electricity infrastructure side, we translate all that predictive knowledge into choosing where we build these offshore wind facilities, how we bring it onto the grid, and then managing power moment to moment so that operators can maintain a stable and cost-effective system when you and I turn on our light switch, whether you and I are in the city or on the coast. We also innovate at that edge of the grid with flagship programs in transactive energy, distributed control, coordination, and tools to plan and optimize across multiple layers of the grid. It's complicated and it involves expertise and cooperation across many disciplines, like Megan mentioned: earth sciences, all disciplines of engineering, computation, economics, from the bench to the lab to the real world. And that's why it takes a national laboratory to tackle these challenges. It's a really exciting time to work in energy research. So thank you for joining us on this tour to learn more about PNNL and how we're going to meet that energy future. So with that, I'm going to hand it back to Megan to get us started. Thank you.
Thank you, Rebecca. Now I'd like to turn it over to Jason Fuller. Jason is going to tour us around the Electricity Infrastructure Operations Center. He joined PNNL as a research engineer in 2009, and he is now the group leader for the Electricity Security Group. Jason, take it away.
Yeah, thank you, Rebecca and Megan. I appreciate that. Welcome everybody to our Electricity Infrastructure Operations Center, or the EIOC for short. It's a mouthful, so I will only call it the EIOC from now on. If you look around here, you can see that this is actually a mock-up of a control room. We use this room as a way to solidify some of the experiments that we want to do. We use it to collect data and information and store it in a facility in the back of the room here. That allows us to do the research that we do at PNNL, really about modernizing the grid and addressing some of the challenges that Rebecca mentioned. And so I'll start here with this kind of first area right here, where this is really kind of getting to the data that we're talking about here. So this is a tool that we actually have with collecting data. It's pulling data in from some utility partners that allow us to have access to that data and do the research on it that we need to do. What you're seeing here is actually a reading of frequency. So this number right here is the frequency of the US power grid on the West Coast right now. And you can see it's moving up and down. That information actually gives us a lot of information about the health of the power grid right now, because as Rebecca mentioned, at every given instant of the day, we are balancing generation and load perfectly. So every time you turn a light switch on, some generator is changing its output to match that change. Now, of course, we got lots of things moving around. So for the most part, it's one big spinning machine that's adjusting over time. But as that machine speeds up or slows down, that frequency goes up and down. Now, as long as our frequency stays around 60 hertz, what we operate here in the United States, plus or minus 0.05 hertz, things are pretty good. There's all sorts of controls that go into place if you get outside of it, and allow us to basically try to bring that grid back into stability if there are ever any big issues that happen. So really what I'm showing here is just that the fact that we have access to this data as a research organization really allows us to bring home the research that we do in a way that allows it to not only make a research impact, but also then get that out into industry and make sure that we're actually driving it in a direction that allows the grid modernization that we're looking for to happen. And I'll talk a little bit more about how we use that as we move kind of down the pathway here. So we get to this next screen here. What you're seeing here is actually a replay of the 1996 blackout. It doesn't look like it, obviously, but it's a tool that we created that helps us actually detect those type of blackouts well before they actually occur. And so what you see here is a playback over the course of about 5.5 minutes, which is about how long this event occurred. You look it up here, this is a power flow across one of the lines in the Western Interconnect. And there was a series of tripping events, or basically faults in the system where certain elements or assets went offline. So one occurred here about 3 minutes in, another one here about towards the end of it. What you're going to see here as this is progressing is that you see kind of these kind of wiggly lines. Those are also related to frequency. They're not frequency, they're power. But right here at this event, right at the very end, this is where the system went unstable and things went very poorly. What it turned out was we actually had information all the way back here at this kind of first event that allowed us to basically say, hey, there's something going on, maybe we can make some adjustments. And so what this tool does is takes data, just like you saw back here. It sucks it all in, does a whole bunch of cool mathematics on it in the background, and then applies it to locate what's called a mode of operation, or this little circled dot right here. What's happening is this mode of operations is basically an oscillation between two big generators in the West Coast. And as long as it's over here in this kind of yellow or green area, we're doing just fine. What we actually could tell about 5 minutes before this event is this started drifting into the red. We didn't know this back in 1996. This was information that we didn't know because this tool didn't exist. But we were able to use the information from those blackouts to then detect or build a new detection method that's now being pretty much deployed across the West Coast in terms of being used by the utilities. What really happens is right as this event hits this last trip where this last line goes offline, you'll watch this dot right here. It'll shoot across the line and it'll go into what we call an unstable territory. And that basically, once that happens, the whole grid starts to protect itself. It kind of pulls apart. In this case, 7.5 million customers went offline for about 6 to 8 hours in some cases. And so what we really try to do here with our research at PNNL is create tools like this that we can actually detect and help utilities not experience that event. Because in the end, what we really want is good, clean, reliable power. And step number one is getting to reliable. And so this is a tool that we've helped create to make that happen. As we kind of move to the next area here, this is something called the North American Energy Resilience Model. This is an effort to go beyond just what we consider reliability, which is looking for immediate failures in the system, but also start to plan for big potential outages. In this case, it's really looking at the fact that our electric power grid now is no longer kind of independent of itself. In the past, it was always kind of operating on its own. It had its own communication systems. It had its own kind of fuels and things like that. But now we're very reliant on natural gas systems, and we're very reliant on communication systems and modernization in those areas. And so this is a tool that was created to start looking at not just the impacts of, say, things like wildfire or weather events or hurricanes, what effect that has on the power grid, but also the things that the power grid relies on. So actually pulling together things like natural gas models and power grid models to really detect, are we sensitive to some of these kind of big events? And if we are, what can we do about them to mitigate this? So this is something that we're working on for the Department of Energy to really kind of highlight how these interconnections are forming over the course of the evolving power grid. And are there ways that the Department of Energy can help to drive us so that we can have a more reliable system as these interconnections grow? These things are actually really positives in terms of they actually bring efficiency and reduce power or reduce the cost of power. But we also want to make sure that as we're doing these things, that we're actually doing it in a way that actually increases reliability and not the other way around. So as we move on to the next panel here, we're talking about what really I think Rebecca got into earlier, which is really kind of exciting, which is the idea that we're moving to a future where there's a high amount of renewable generation. The challenge with renewable generation is that as we start to get the high penetrations of it, we are used to operating the system with what we call spinning machines, or machines that basically have coal or natural gas or some kind of readily available resource that we can basically tell the generators how much to put out. That gets back to your question or the comments about frequency. So as long as you can have a controllable generation source and you can move things up and down, we can track all the changes in the power grid and then keep that frequency squared away. The challenge with renewable generation is that we don't control the fuel source. When the wind blows, the wind blows. When the sun's up, the sun's up. And lacking a storage capability, we have to keep balancing those things. So one of the things that operators do is they keep what they call spinning reserves, or generators that are just sitting online just in case another generator goes away or in case load suddenly picks up. With wind, in this case that we're looking at here, this is what we call the wind ramping tool or the wind uncertainty tool. It's really trying to help operators predict how much wind is going to be available in the next 20 to 25 minutes. And so the reason we want to do that is because if you suddenly have a complete kind of loss of wind blowing in your region, you can have a complete die-off of the wind output, and therefore you have to backfill it with spinning generation, which is really generation you're paying to just sit there and idle just in case. And so that can be a real kind of cost-sensitive question in terms of, are we keeping that resource online for a good reason? And what this tool has done, and we worked on with this tool with a utility partner, and has now actually gotten moved out into a number of other utilities for demonstration. But it was actually to help them forecast the bounds of what that future looks like. And so you see here on these kind of slopes out here, these gray lines, these are actually a probability curve to say what's the likelihood of us having enough generation from wind, and then what's the shortfall. And so you see these yellow lines here, what's the potential shortfall that might occur. And so this tool is used so that the operators and dispatchers can actually have better predictability about where that wind is going, and then be able to make changes in that in a way that allows them to reduce the amount of overhead that they're basically reserving for these reserve generators. And so this is something we've deployed. We've actually worked with utilities to test it out further, but indications are that it could potentially save millions of dollars in just operational fuel costs. And so really excited about this. Behind all this is, of course, a whole bunch of things like machine learning and data analytics, bringing in data sources from all over from climate predictions, weather predictions, pricing predictions, fuel resources, to really pull this into one visualization that someone can then interpret as what they need to do next. And finally, I'll move to the last kind of little slide here. Just talking a little about PNNL's leadership in this space. And so when we talk about it from the perspective of grid research, PNNL is by and far one of the largest laboratories that do work in this area. Rebecca mentioned we have about 350 people just in our division alone that are doing energy research. It's pretty exciting times. We actually lead what's called the Grid Modernization Lab Consortium with the National Renewable Energy Laboratory, where we're actually looking at trying to coordinate all of the grid modernization efforts across these 5 offices within Department of Energy to make sure that we're actually bringing in coordination and being good stewards of the American taxpayer money to really drive this grid modernization effort forward and make sure that we get to a clean, reliable, and flexible power grid of the future. And with that, I think we have time for some questions.
Great, thank you, Jason. We'll go ahead and move right into Q&A, and please feel free to continue asking your questions through the chat window. We also have Emily Barrett on the line to address your research or your questions as well. Emily is a senior power systems research engineer and team lead of the resilience team. So let's go ahead and get started. We seem to be seeing more and more major weather events that result in larger and longer term blackouts. Are there ways that PNNL's grid work can help the power system perform better under these kinds of extreme weather events, or also things like wildfires?
Yeah, Emily, would you like to take that question?
Sure. So I think, I'll go back to some of the capabilities that Jason already mentioned and then maybe mention a couple of others, but the answer is absolutely yes. So one of the tools that Jason talked about was NARM, the North American Energy Resilience Modeling Program. And that's a tool and a program that we've stood up to help us prepare energy infrastructure in this country better for these kinds of extreme events. And we can do that in several different ways. So there's long-term planning measures that we can take to understand how do we better prepare our system for these possible threats. So how do we create the necessary, how do we harden our systems and create the necessary redundancy and make these systems more able to withstand things like wind and icing and fire. And then there's operational things that we can do in closer to real time. So, it takes years to put some of those longer term measures in place, but sometimes there are actions we can take the day before to make sure that we're better able to withstand these events as they come through. And that can be things like, isolating portions of the system or changing the way that we match our generation and our load to provide better redundancy and better resiliency to those anticipated threats. So we're doing that in North America broadly through the North American Energy Resilience Modeling Program. We've also done that in support of particular entities in the system, for instance, after the hurricanes that hit Puerto Rico.
Great, thank you. Do you test your tools on local grids at the small scale?
Yeah, so, it depends on the project, of course, but as much as possible, we try to partner with industry and with utilities to make sure that we're getting these tools out into the industry to make them impactful. So as Jason said, we sometimes do that working with utility partners at a large scale, like across the Western United States. We've done demonstration projects. We did a transactive demonstration project in Washington State several years ago that looked at new ways that we could operate the system and be more responsive and allow loads to be able to participate more in helping with cost effectiveness and decarbonization in the system. So the answer is yes. We try to partner as much as possible with the industry and get our tools and methods out of the lab and into the real system.
Okay, and then I think, Jason, this may be related to one of the screens you were showing. Are the 2 large generators in the West both nuclear generators?
That's probably an oversimplified description of what it is. It's more areas of generators or groupings of generators that interact with each other. Basically, each generator is a spinning machine, and so it's spinning at a certain frequency. The power grid in the West Coast is all one big power grid, and that means that all those generators have to spin together at that same 60 hertz. And so what happens is there's certain pathways along the transmission system that have a certain characteristic that makes it so that those groupings of generators can potentially start to oscillate a little bit around that 60 hertz. And so you can think of these as like subfrequencies or things like that. And so in this case, this was not a single generator or single two generators, but it was a groupings of generators. I couldn't specifically tell you if one of them were nuclear or not.
Okay, thank you. Do you research the mix of energy sources, like the percentage of wind versus solar versus others?
Go ahead, Emily.
Yeah, absolutely. So, I mean, we do this from a couple of different perspectives. So one of the things that we look at, because there's a lot of different ways that you want to tackle that question. A lot of the time when we're asking the question of, well, what is the value of different possible fuel mixes? You know, that the question is, well, how do we get to a point where we have more clean energy on the grid, for instance? Or how are different energy mixes more or less resilient to certain threats? So one of the things that was a big driver for the North American Energy Resilience Modeling, the NARM project that I talked about earlier, is that we have more and more natural gas in this country. I think we're up to about 40% in 2020 compared to, I think it was 15% 20 years ago. And so that's a big shift, and we need to understand, what the impact of that new increased dependency on that fuel type is, because it affects the way that we have to operate the system, and it affects potential vulnerabilities. So, an increased dependence on natural gas, for instance, means that we have to understand how those two infrastructures interact in order to understand, how things like a major cold event might affect our ability to operate the power grid. And we do the same thing with things like renewables. As we have more and more renewable energy coming online that we can't necessarily dispatch and control in the same way that we have some of our more traditional natural gas, coal, nuclear resources, we need to understand the impact of that to make sure that we're doing that in a way that maintains the reliability of our system. So yes, absolutely. That's a really important question.
Okay, and how much is this year's drought affecting power availability? Is it affecting the cost of power?
That's a great question, and it's particularly relevant here in the Pacific Northwest. So one of the things that we are blessed with in this part of the country is significant hydro resource. So we have a lot of really flexible, clean hydropower that we are able to use in our system that helps up across the board. One of the concerns about droughts is that impacts that resource. So as we see, more and more drought conditions in the Western United States, there is a concern that that's going to impact our ability to produce hydropower, because if the water's not there, we can't run it through the dams. And there tends to be some delay. So, the drought year, you might start to see those impacts cascade slightly later. But yeah, that's absolutely something we think about and study. Anything you wanted to add to that, Jason?
No, that was a great description. I think, the other concern around droughts is really just the danger around that it produces around wildfires. And of course, a lot of those wildfires are located around critical infrastructure like our power grid. And so, some of the concerns, of course, right now are, about tracking and understanding what is the potential for some of those fire dangers, both from sources like lightning, but also from things like transmission lines. And so some of the work we do here is to try to help understand things like vegetation management and what is risks associated with wildfires from transmission lines, and help the utilities prepare for those type of events.
Thank you. And is this facility used to train people?
Well, that's a great question. We have used this facility a number of times for training, mostly because of the facility. It's something that's not normally operational, so we can use it for utilities to come in and do certification training and things like that. We have used that in the past. And the even more exciting part is then we can kind of take that next step and say, that was good. You were able to do your training, but can you stay for another extra half a day and do some experimentation with our stuff and see if it would have been different. And so that's something that we've been able to partner with both the vendor and the utility community to really kind of not only provide a space where that can occur, but also then to use it as a research piece to help develop and drive our tools in a direction that is useful to industry.
Okay, and it seems as though the emphasis is still on macro grid interconnects. When would you see the nation moving towards a wider set of smaller interconnected mini grids or even microgrids?
Yes, that's also a great question. And you know, there's a possibility of going many different ways in that. You know, if we start looking at grid infrastructure 20 or 30 years in the future, there's certainly a possibility towards going towards what you call the macro grid, or there's a possibility of looking at much smaller kind of microgrid communities. And of course, the challenge with that is that there is some advantages to economies of scale. The idea that lots of big resources connect together are typically cheaper than smaller resources. The bigger macro grids tend to be more reliable because you can lean on your neighbor when something goes wrong. So an example of that is ERCOT or Texas over this last winter, where they did not have the possibility to lean on their neighbors. They don't have as much transfer with other parts of the country, whereas just north of them in the Midwest, they were able to lean on other parts of the country, particularly the East Coast and the Southeast, to weather through some really cold storm fronts. And so there's some real advantages that come from a macro grid or an interconnected grid, and that's why we've moved this route in the United States. That said, there's some really interesting operational desires and needs around microgrids. And some kind of combination of a microgrid system where you can operate locally, but then also be able to connect to the larger system has a lot of advantages. And so there's quite a bit of research here at PNNL that's working on both the operations of those small grids, but also more importantly, how to make sure that they can connect to the macro grid and operate at both scales, depending on the needs of the system at the time.
Thank you. Given the time lag from East Coast to West Coast, can we ever have a single unified 60 hertz national grid, or will we have to go more high voltage interties?
Emily, do you want to take that one?
Yeah, I will, though I'm not going to say that I have the definite be all and end all future telling answer. I actually think that the time gap between the East Coast and the West Coast is an advantage when you think about operating it as a macro grid. One of the challenges in the power system is that sometimes we produce energy at different times than we're consuming energy, and sometimes time shifting actually helps a lot with that. So if you have part of your system peaking at a different time than another part of the system, you can sometimes better utilize your generation resources. So we tend to use less power in the middle of the night. We tend to use a lot more power, right after people are getting home from work. In the summertime, we tend to use more power in the middle of the day. So having a diversity of load and climate in your grid can actually be a big advantage. The challenges behind making one gigantic North American system are largely the operational boundaries that exist today, and the amount of effort and money and investment and change the way that we operate that would have to occur to be able to make those two systems operate together synchronously. So some of what we've looked at as opportunities are ways to connect these systems in other ways. So to take advantage of some of those time shifting opportunities, and that sort of load sharing and balancing opportunities the way that Jason was discussing, without necessarily introducing the additional complexity of operating, the East and the West together in a single 60 hertz synchronized system. And so that's more things like these macro grids where we have, big transmission lines that allow us to send power back and forth, but do not require that these systems operate in the same interconnected synchronous system.
Okay, does lightning strike power lines? If so, how is the grid protected from the burst of electricity?
It does.
Yep, go ahead.
And we have automated protection systems that respond to that very, very fast to prevent. So basically, we have protection systems that are specifically designed for lightning strikes, and that is to prevent arcing and to prevent that from causing larger cascading problems in the system. So yeah, they're very fast acting automated systems specifically designed for lightning.
Okay, and I think we have time for one last question. Following up on the microgrids, there's also microgeneration as far in other words, home solar. Can that be modeled for resiliency?
Oh yeah, absolutely. And in fact, that's something it's a way that the power system today is changing from a way it operated 10, even 5 years ago. And so part of the work, I think, when we talk about, say, for example, tools like NARM, but also other tools that we develop here, we are using it to model both the large generation systems, the transmission, high voltage systems like that. We also do quite a bit of modeling on the distribution side, which is kind of the low to medium voltage kind of side, all the way down to the voltage that's inside your house. And so one of the questions that we're trying to answer today is, how do you integrate those, what we call distributed energy resources, or DERs, which are small generators or small storage systems, or even things like electric vehicles? How do you integrate those into the operations of the power system in a way that allows for smooth operations? The utilities still need to keep the lights on, but we as producers of that power, if it's behind our meter, we want to be able to put that back out into the power system and have it be used when it's needed. And so a lot of our research is focused on what's the mechanism for doing that, both from an operational perspective, but also from a transactional or money, like how does money exchange hands kind of question. And so both those kind of areas of research are pretty fruitious right now, are pretty doing a lot of that kind of work, and we're pretty excited about where it's headed.
Great, thank you, Jason and Emily. We appreciate you taking us on a tour of the Electricity Infrastructure Operations Center and answering those questions. We had a lot come through, and unfortunately we weren't able to get to all of them, but thank you. Now I'd like to turn it over to Joshua Lakala and Cassidy Anderson, who will take you on the second part of our tour. Joshua and Cassidy are both materials scientists in our Energy and Environment Directorate, and I believe Joshua is going to start off the second tour, so go ahead, Joshua.
Yes, thank you. We are in this lab. This is the high throughput energy lab. PNNL is really striving to be one at the forefront of finding the better battery. And what that means is we utilize our knowledge in cutting edge material science, as well as understanding the application and the end user requirements for these batteries. Now, that application can be anywhere from grid storage to electric vehicles. So we utilize this knowledge to identify new materials, new combinations of chemistries, as well as new configurations of the battery in order to realize this better battery. So not only do we want to know or have these new materials and new combinations, but we want to have the tools, the analytical tools, to say these materials are better and to have that value assessment. One of the things that this lab does is it utilizes knowledge to find materials for flow batteries. So you may think, what's a flow battery and how is this different? So flow battery is actually very different from a car battery or a cell phone battery. Instead of a solid, it uses a liquid. It uses what's called an analyte and a catholyte to cycle that battery and to store that energy. But a flow battery is very good, but it has a lot of different chemistry combinations because it's just a redox reaction. So we need to be able to identify these different materials that can be utilized in a flow battery setting. So that's where we utilize artificial intelligence and machine learning. This will comb through all of these different chemistries and combinations to find the ones that are low cost, high duration, so it can cycle for a very, very long time, and high capacity. Once we go through this artificial intelligence and this computer learning to identify these things, well, we need to test them. But we've got all these thousands of combinations that seem to be good. So we utilize Albert and Beverly. These two machines are actually robots. And their real name is the High Throughput Experimentation System. We thought about calling them HTES, but that really doesn't roll off the tongue as good as Albert or Beverly. And so right now, these machines are going to go through all of these combinations that we found to be potentially high power, to give us that capacity that we want and the low cost. Because right now, a lot of the flow batteries use what's called vanadium. Vanadium is a rare earth metal, very, very expensive. Okay, Joshua, you say vanadium, you say you've got this combinations. What's the practical application? Well, actually, one of the things that we found is fluorinone. So fluorinone is a general organic compound that we've seen used in a lot of different industries. What we found is that fluorinone can be utilized in a flow battery setting, but there's thousands and thousands of derivatives of the fluorinone. And also fluorinone is not soluble in water, and we need to utilize water for a flow battery. So our scientists at PNNL, with the use of Albert and Beverly, have found the derivative that is soluble in water. This has given us an increase in capacity, 2 to 3 times as much as vanadium, and it's significantly cheaper. And that is one of the reasons why flow batteries are utilized for grid storage. They're scalable. So they can be as large as a train car because of the fact that they utilize materials that are cheap and accessible. Okay, we've got the materials, we've identified it, we've shown with Albert and Beverly that it works really well. PNNL does not stop there. PNNL then sends it off to different labs. They scale up even larger scale, do more rigorous tests to simulate what this would look like in a grid setting. And one of those things, once it even gets past that, PNNL has collaborated with Energy Northwest, which is an energy collaboration, and Tucci Energy Services, which is a Seattle energy company, and worked in collaboration with this Horn Rapids Solar Storage and Training Project. This is partially funded by Washington State's Clean Energy Fund, with the goal of demonstrating that photovoltaic solar combined with our batteries can deliver predictable, reliable, clean electricity. But it doesn't stop there. This project also provides the training for those technicians that will put this into the real world to be able to manufacture these large-scale batteries, to repair them and maintain them. So PNNL is in every aspect of the flow battery, but we don't stop at flow batteries for electric grid storage. We also do electric vehicle. And I'll pass it over to Cassidy Anderson, who will discuss our research in vehicle storage.
Thanks, Josh. So what I have here is a cylindrical lithium ion battery. So in today's electric vehicles like the Tesla Model S, you'll find roughly 7,100 of these cells used to power the car. So now here at PNNL, the goal of our Battery 500 consortium is to develop a battery that can more than double the cell level energy of these traditional lithium ion batteries. Now, regardless of the chemistry that we use inside these cells, we will have to use a lithium metal anode in the battery. So for this reason, our consortium only focuses on high energy lithium metal battery technologies. So our consortium has 4 national laboratories, 5 universities, and 10 seedling projects across the US. We also have an industry advisory board to help monitor our progress and participate in research and development. You'll recognize some of these logos here: Tesla, IBM, also USABC. GM, Ford, and Chrysler are all a part of USABC, so they're on our industry advisory board as well. So like I said, in order to double this energy capacity, we're gonna have to use a lithium metal anode, and these have some challenges. So that's why the consortium has assembled world-class researchers to tackle these issues. So this picture here is from a 2018 quarterly review meeting. Just 1 year later, in 2019, 2 of the PIs pictured here were awarded the Nobel Prize in Chemistry for their outstanding contributions to lithium-ion battery research. So it's pretty remarkable that we have 2 Nobel laureates researching in our group. So all of the battery research that we do here is application-driven fundamental research. So what this means is any new materials, ideas, or technologies are all validated using realistic pouch cells and put through our rigorous testing protocols. So when we're moving away from lithium ion battery technology and towards lithium metal battery technology, we have to redesign all of the cell components so that they're compatible with each other. So what's inside our cell? Every battery is going to have 2 electrodes, our anode and our cathode. We're also going to have some sort of electrolyte in between them. We will then use some sort of separator material. And then finally, we'll wrap it in some sort of cell packaging. So what I'm holding here is a prototype lithium metal pouch cell battery developed by the consortium. This one has achieved 400 watt hours per kilogram. That already is a 70% increase in cell energy when compared to today's current lithium ion batteries on the road. This cell has also achieved record cycling stability when compared to any current published literature results. So this was all accomplished by the consortium in the past 3 years and wouldn't be possible without the contributions of all of the team members involved. So now I'm going to walk you over here. Not only do we have world-class researchers, we also have access to world-class tools. So what we're looking at here, this is an in situ characterization image gathered by our researchers here. So what we're looking at, this is a nanoparticle that can be commonly found in our advanced battery materials. And what we're watching is what happens to this nanoparticle during charging. And so we can see here that as the battery charges, this nanoparticle actually breaks apart, part of it splits off, and it falls apart. So this is bad news for your battery if your materials are breaking while it is cycling. But here at PNNL, we have the advantage of knowing that this is happening inside of our cells. So our researchers are able to go back, redesign these materials to accommodate this large volume expansion and put them in a battery that ultimately is going to perform better. So once we have these new redesigned materials, we take them, assemble them into our pouch cell batteries, and now cross-validate them to make sure that when the technology is ready, it can be easily adopted into industry and is ready for commercialization. Thank you. I think we have time for Q&A.
We do, and thank you, Joshua and Cassidy. The first question is, how environmentally sustainable is fluoronone, especially compared to vanadium?
It's highly sustainable. So fluorinone is just an organic compound. So anytime you're doing fractionization of oil that you would use, you would get these organic compounds and you can synthesize it. Whereas vanadium is a rare earth metal. So for example, fluorinone is about 0.23, so 23.23 cents per gram, as compared to vanadium, which is on the dollar scale per gram.
Great, thank you. And did your program ever work with the MIT offshoot company Ambry that Dr. Donald Sadoway co-developed to commercialize the liquid metal battery?
I do not know.
Okay.
Not that I'm aware of, no.
Okay. All right. So why do you use lithium metal and how is that different than what is in a lithium ion battery?
Yeah, so I would say there's 2 main reasons that we use lithium metal. So in a lithium metal battery, your anode is pure lithium metal. This is different than a lithium ion battery, where your anode is usually some sort of graphite or silicone material. When we're comparing graphite and lithium, lithium has 10 times the theoretical capacity of graphite. So this means we can get a higher energy out of our battery. The second reason being, if we look at the periodic table, lithium is right under hydrogen. Its atomic number is 3. So it's just a lot lighter in weight than carbon, which is what our graphite materials are made out of. So that means we can achieve a higher gravimetric energy density.
Okay, thank you. And how well do iron-based flow batteries work?
Iron-based flow batteries work pretty well, but we still run into the issue of we're utilizing, while iron is not as expensive as the vanadium, if we can get something that is a little better and cost effective, that would be better. The benefits of iron is that we could, there are work being done at doing the two electron steps instead of just one electron step. So there's some cases in which it can have a higher capacity, but sustainability is always an issue.
Yeah, our floor nodes are just carbon, hydrogen, and oxygen, so easier to obtain.
Okay, and how are the applications of redox flow batteries different than pouch cell batteries?
So redox flow cell batteries, as I mentioned, they're very scalable, and they utilize a liquid electrolyte, which is aqueous based. And so because we just utilize a liquid, we can have two massive containers of the analyte and catholyte. And as long as the material that you're running the analyte and catholyte through doesn't degrade, it is very, very stable. We don't have to worry about the plating and stripping of actual metals, where we're just utilizing ions in a liquid. And so for large scale applications, this is very beneficial. As you can imagine, because we're using water, the gravimetric energy density is very, very low. So gravimetric energy density is just how much energy can we put out per gram or per kilogram. And so if we think about using lithium, which is very, very light, versus water, which is very, very dense, we already see the problem. But each one has its different application, and so that would be why we would use redox flow batteries for those stationary batteries, rather than the ones that we need to put on cars, in which we're limited in the amount of weight a battery can be.
Okay, and are any new or upcoming manufacturing or packaging technologies likely to impact the cost, longevity, or energy density as opposed to the internal chemistries?
Oh, yes. So when you think about like a lithium metal pouch cell, every part, every component of the battery is important. So for example, if we use a very thin piece of lithium versus a thick piece of lithium, that will go into the total weight of the battery and our gravimetric energy density. If we utilize a material that separates the cathode and anode, that has different pore size, that allows electrolyte to go through differently, so the chemistry doesn't change, but these are affecting the mechanics of the battery. So everything that goes into the battery has an effect. Are we using a really thick cathode? Are we using a thin cathode? You know, how much electrolyte are we using? Every aspect is optimized for the performance, and that includes the material that we put it in. So if we have a thinner pouch that we put the actual cell in, it will decrease the weight and increase the energy density. However, does that increase the risk of electrolyte leaking and your battery dying from electrolyte leaking or catching fire? So everything is a balance, but it all goes into the final form of the battery.
Yeah, and I'll just add on to that pouch cells and cylindrical cells have been in production for decades now. So most of our weight cutting and energy increase is going to come from improving the materials inside of the battery. Like Josh said, we can manipulate the cell packaging thickness or maybe the shape, right, cylindrical or pouch cell. But since that has been a known process, we've optimized it for the most part. So any major improvements are going to come from what's inside the battery itself.
Thank you. Could lithium ion batteries in a system be swapped out with lithium metal batteries as an upgrade?
Yeah, so a lot of the applications that we're looking at for lithium metal batteries, it's where we need a lightweight, portable, high energy battery. That's really what our current lithium ions are used for, right? Your cell phone battery, or you don't want something large and bulky. Also, electric vehicle, where you really are considering weight, and you also need a higher power for longer range. So yes, definitely our lithium metal battery research is looking to replace and upgrade current lithium ion battery applications.
Thank you. Do you see the possibility of batteries advancing enough in the future to be able to power airplanes?
It's a good
Of
question.
course, yeah. That would be the ultimate goal. Right now, that's where the energy density comes in. Airplanes typically have very strict weight controls. And so balancing the weight and the energy output of the 4 turbine engines, right? For example, on a 757 versus the amount of weight adding all the batteries that you would need to power that for long periods of time. So there's definitely a power to efficiency ratio and the power output to provide lift, as well as the weight of the battery versus the weight of jet fuel, and so on and so forth. That the potential is there. We're never going to say we can't build a battery for that, because we're going to try, but we may be a little bit farther into the future than we would hope.
Okay, and then for redox flow batteries, can you recharge the solutions with electricity, or are you replacing the chemicals with each use?
No, that is completely rechargeable. So for example, that fluorinone system, they cycled it. So complete charge discharge cycle is considered one cycle. They cycled it, charged it, and then recharged it over 1,000 times with only a 3% loss. The only reason why the battery failed was not because of the electrolyte, the analyte, or the catholyte. It was actually the parts that were the mechanics of the parts that are running the battery, not the battery itself.
Okay, and what are some of the problems for utilizing batteries at the grid scale?
So one of the things that we need to worry about when we're utilizing batteries at the grid scale is obviously how quickly we can get that charge out and recharge the battery. For example, lithium metal batteries, one of the problems if we were utilizing them, not only is the amount of materials, but it's how quickly we can charge it. We run these batteries under strict charging because of the problems with lithium metal. Now, the same thing would be said with like redox flow batteries, that the amount of charge you can get is greater. We don't have to be as stringent, but you're always trying to optimize how much charge you can put in and how quickly you can get that charge out. So you're definitely looking to store the energy and work with the power companies as our previous work, that would be all integrated into the system to where we're optimizing the amount of charge we can pull out and how quickly to maintain the battery life. So that's a lot of battery management system research that's needed. There's still chemistry research as well, but a lot of that is battery management, how quickly we can pull in, how quickly we can pull out, how big we can make them, and so on and so forth.
And I think when you're talking about supporting the grid, there's if you're talking about covering an outage that's just lasting a couple of seconds or a couple of hours, right? Those are going to be different battery technologies. Just like lithium ions, the chemistry, even though it's a lithium ion battery, what's in your power tool is different than what's in your cell phone because we need different energy release over different durations of time. So when you're talking about grid storage energy, you also have to look at the time and the power output that you need from that battery, and those are most likely going to be 2 different batteries.
Okay, and we have one more question here. I read that lithium, nickel, cobalt batteries degrade after a few hundred cycles, whereas lithium titanate can cycle tens of thousands of times without degradation. Why do we not hear more about lithium titanate developments?
That's a good question. So lithium, cobalt, nickel oxide, so NMC, we routinely use these cathodes and couple them with our lithium metal anodes, but titanate, I have not heard about that. So I guess that is a good question why it's not talked about more, since I don't think either of us have heard of that before.
And the other thing I'd like to mention is NMC does. It's a little bit of a leading question because NMC doesn't degrade as quickly as that question would perceive, right? So we can cycle NMC with very high capacity retention.
Gassing.
And so and if it battery failed, it's not going to be from the NMC, it's going to be from the anode side. So there is some of this high nickel work does have some issues, but the problem in that utilization is not from the cathode side, it's going to be from the anode side.
And another thing we have to consider in our cathode materials is what are the products formed when we have reactions between our electrolyte and our cathode. So the possibility is that there's different gaseous compounds formed in these other cathode materials that make it a less desirable cathode.
Okay, thank you. And thank you to Joshua and Cassidy, and thank you also to Rebecca, Jason, and Emily for the great tour, the information, the time to answer the questions to help us better understand the electric grid and energy storage. And thank you to all of you who took time out of your busy schedules to attend tonight's tour. At this time, I'd like to ask everyone for just a couple more minutes out of your day to take our brief survey. The survey link will be in the chat window here momentarily. And at the end of the survey, you can also sign up to receive notifications about future tours, seminars, and other community events. We also have recordings of past events that you might be interested in, which can be found at pnnl.gov/events. I'm going to share my screen here really quick. Wanted to share information on our next virtual tour. It is PNNL and National Security, 20 Years of Mission Impact, and it's taking place Wednesday, September 8th at 5 o'clock. On this tour, we will visit 2 facilities at PNNL that have provided the Department of Homeland Security with world-class solutions in airport security scanning and radiation detection at U.S. ports of entry. You can register using the link in the chat window. And you can view more information about all of the upcoming tours on pnnl.gov/community-tours. Thank you so much to everyone who joined us tonight. We hope to see you next week.